Welcome back to Advanced Machine Learning. I'm Ludwig Botmann, and in this video we will speak about SMOTE, a specific oversampling technique. SMOTE creates synthetic instances of the minority class. So this is not a random oversampling, but we are creating new instances that are not in the dataset. This is done by interpolating between neighboring minority instances in the feature space. Okay, so we are just looking at the feature space, not at the combined feature and target space. The basic algorithm is as follows, and I will explain on the next slides a little bit more the details of this. First, we have to find the k nearest minority neighbors. Okay, so this is about upsampling the minority class. So we are creating new instances of the minority class. So first, we find the k nearest minority neighbors of a specific example of the minority class. Then we randomly select one of these neighbors, and then we generate new instances along the lines connecting the original minority example and its selected neighbor. How is this done? Here are some formulas for this. So let xi be the feature of the minority instance, like the base minority instances that we want to upsample, and xj is one of these k nearest neighbors. Okay, so one random example of its k nearest neighbors. The line connecting these two instances is, of course, 1 minus lambda times the feature vector of I plus lambda times the feature vector of x, or of observation j, so xj. We can rewrite this as the sum of the feature vector plus weighted difference of the two, which is just exactly the same. And lambda should be something between 0 and 1, so we are doing a convex combination here. And now we sample 1 lambda and call this lambda tilde between 0 and 1. And with this we create a new instance. So x tilde I is then the sum of the original data point and the weighted difference of the two data points. So here we have one example, x1 and x2 on the x and y axis, and we have two instances, 1, 2, that one here, and 3, 1, that one. And the new instance is, assuming lambda tilde would be 0.25, this point here on the line connecting those two instances. So now we've prepared a thorough visualization of this. So we have an imbalanced data situation, and we take 4 instances of the minority class. Okay, so all the 4 points you see on this slide or in this plot are instances of the minority class. We do not look at the instances of the majority class at all. And we're doing k equals 2 nearest neighbors, just for having a good value for visualization here. Okay, so we start with a one selected point. That's that one here. So this is just for your reference. On the previous slides, this would have been xi. And then we computed 2 nearest neighbors without the point xi itself. In that case, so these 2 points are the 2 nearest neighbors. And then we select one of those 2 nearest neighbors. In that case, that one here. And we create a synthetic data point on the line connecting the original data point and one of those 2 nearest neighbors, and end up with this new data point here. So in the end, we have 5 points of this, with a resulting data set of 5 points. Now we can do this again and choose, for example, that point here as xi. The 2 nearest neighbors are those 2 here, and we select, or we create a new point on the line between those 2 here. And we can do this over and over again, also for this point, which is a little bit further away. So we start with 4, 4 here, two nearest neighbors. Those two we select as random selection of those two, that one, and then we have a new data point in between those two here. And doing this over and over again, we get a lot of new points, and as you can see, all these points are on straight lines between original data points. Okay, so we have 1, 2, 3, 4, 5 lines here, and all the new points lie on these, on one of these 5 lines. We could do the same thing for k equals 3, which means that in the end we can also have points on that line here, because those two are furthest away from each other. They never been in the two nearest neighbor set. So then in the end we have points on those 6 lines here. This was a very small but I hope illustrative example here. Now let's turn to a real dataset example using the iris data. We have 3 classes in the iris dataset, 50 instances per class, so that's not imbalanced at all. It's perfectly balanced. But we can imbalance it somehow by relabeling one class as positive and 2 other classes as negative, just to have a further visualization here. And you see the relabeled data on the left-hand side here, 2 classes. And yeah, let's perhaps start on the right-hand side. Here is the SMOTE data set with k equals 1, which is good to see here because we also have just these straight lines here between original data points. Okay, and then with k equals 5 in the middle, it's a little bit more general. So we have chosen more representative examples, perhaps let's say from the minority class here. And what you see is that SMOTE enriches the minority class feature space. So let's say the minority class feature space is just everything on that side here, on the upper left hand side of this separating line or hyperplane, and then the SMOTE algorithm enriches this part of the feature space but leaves the remainder, so the other part, that part of the feature space, unchanged. So some disadvantages and advantages of SMOTE: it generalizes the decision boundary for minority class instead of making it quite specific, such as by random oversampling. So what does this mean? Random oversampling will just create new instances, which are instances we have already seen before. So rather than exploring the feature space a little bit more, where you're just piling up observations on top of each other so that we balance in the end the data set, but we don't really explore the minority class feature space region at all. It's really well performing, so a clear advantage of SMOTE, and it's a basis for many other oversampling methods. There are over 90 extensions, for example, borderline SMOTE and LN SMOTE. One disadvantage is perhaps that it's prone to overgeneralizing, as it pays no attention to majority class. As you've seen on the last slide, we do not look at all at the majority class, but we're just exploring the minority class. As final slide here, I want to show you a comparison of different sampling techniques. We use a binarized version of the opt-digits dataset, which is a dataset for optical recognition of handwritten digits. So originally it has 10 classes, 0, 1, 2, 9, but this is just the binarized version where the largest class is the positive class and all the other classes are combined in one negative class. We then use different sampling techniques. So as a baseline, no sampling at all, and then undersampling, random oversampling, and SMOTE. And we can compare the performance of random forest learner on these 4 resulting data sets. Random forest with 100 trees, we use 5-fold cross-validation and the F1 score. And in the second column here, you see the resulting class ratio. So in the first line, with no sampling technique, the class ratio is 0.11. And then we oversampled the minority class to these other three values here in undersampling, oversampling, and SMOTE. And of course the question is, at which ratio do you want to set this? So you could just set it to 1 and say, okay, we want to have as many minority class instances as majority class instances. That's one option, of course. But you could also consider this a hyperparameter of your learning process and tune it. So we have done the latter thing. We tuned it somehow a little bit manually, let's say. So we ended up with different class ratios for the three different techniques here. And then in the last column, you see the resulting F1 score via 5-fold cross-validation, of course. And you see that every sampling technique is better than no sampling, and that SMOTE is a little bit better than random undersampling and random oversampling. But yeah, the difference is not that huge here in that example. But still, SMOTE leads the sampling techniques here. Okay, that was it for sampling techniques.